Hey guys, welcome to my channel TechRenaissance, where we talk about the latest and the greatest in the world of artificial intelligence, deep learning, computer vision, and virtual reality. My goal for this channel is to build a very strong community in these areas where we learn from each other, do great things together, and help each other out. I will come out with videos, demos, and tutorials every week, so if you decide to like and subscribe, I would highly appreciate your support. So let's go ahead and get started on this video. I just got the access to the Mojo Playground. I access Mojo Playground by either clicking this link or directly going on Modular website, where you can click on Docs, click on Try Mojo, and go to login. Either way, it will take you to the same link. Remember guys, the Mojo Playground is a Jupyter Hub environment in which everyone has access to the same Mojo standard library, but each user has its private volume in which you can write and save your own Mojo programs. There are a handful of example notebooks to show you the Mojo basics and demonstrate capabilities. Mojo doesn't have its local development environment yet. The Mojo standard library, compiler, and runtime are not available for local development yet, because it's still a work in progress. So we just have a hosted environment here where we can just try it out. That's called Mojo Playground. Let's go ahead and take it for a quick spin. On my sign-in screen, when I click here, it takes me to login page. Now, remember, before you do this, you have to be in the waitlist. Once you're approved and you're assigned your user volume, then you can go ahead and log into Mojo. So as soon as I log in, it will tell me that my server is starting up, and it will take a couple of minutes. So we'll just wait and watch and come right back. Alright guys, so now my Mojo server is up and running. So in this video again, I'm going to compare the performance of Python and Mojo and do a speed test. Right? I'm using one of the notebooks provided by Modular for matrix multiplication, where we will start a basic matrix multiplication, then optimize the code by adding types to the Python implementation, vectorizing the innermost loop, and parallelizing the multiplication function. Each time we update the code, we will compare the performance of Mojo and Python. I'm using the same hardware for running both Python and Mojo implementations to make sure that we're comparing both on the same compute. Mojo Playground runs on a fleet of EC2, C6i, or C6i 8x large instances that are divided among active users. Due to the shared nature of the system, the number of CPU cores provided to the session may vary. So with that being said, let's go ahead and jump into the notebook. The notebook describes how to write matrix multiplication algorithm in Mojo. We will start with basic matrix multiplication and optimize the code by adding types, vectorization, parallelization, and see how Python and Mojo implementations compare. Again, this notebook is provided by Modular. I will not go in details for every single step, since I will be covering a lot of these in my upcoming Mojo series, which I haven't officially announced yet. We will measure the performance of both Mojo and Python in gigaflops per second. The full form, or flops, or FLOPS, is the floating point operations per second. FLOPS is a measure of compute performance useful in the field of scientific computations that require floating point calculations. Gigaflops is a unit for computing capacity equal to 1 billion FLOPS, or floating point operations per second. A higher GFLOPS per second value means that there is a faster compute performance, or the computer can perform more of these operations in less time, and therefore more powerful. So let's go ahead and get to the first cell. This is a Python function for matrix multiplication. The function matmul_Python takes three matrices as input, C, A, and B. It populates matrix C with the result of the multiplication of matrices A and B using the standard mathematical method for matrix multiplication. It iterates over each cell of matrix C and calculates the corresponding value based on matrices A and B. Now, if you don't know how matrix multiplication works, I'll probably make another video on that, or there are a ton of other videos available on YouTube that you guys can refer to. Matrix multiplication is important in a lot of computer vision applications that include multiplying pixel values of images. It is a compute-intensive process. Again, I'm not going to go into a lot of details here in this video, since my goal is to just compare Python and Mojo. So I'll go ahead and do that real quick. The next cell defines a matrix class with constructor and accessor methods. The class takes a 2D list value, rows, and columns as input and creates a matrix with these attributes. The getItem and setItem methods are defined for accessing and modifying matrix elements. Then it defines the function benchmark_matmul_Python, which creates three matrices, A, B, and C. A and B are filled with random numbers, and C is filled with zeros. It uses the timeIt function to measure the time taken to perform matrix multiplication of A and B using the matmul_Python function defined earlier. This operation is performed twice and the average time is computed. The function then calculates the number of gigaflops that the matrix multiplication operation achieved. The result is printed and returned as a float. The last line calls this function with matrices of size 64 by 64 and converts the result into a float 64. So let's go ahead and run the first three cells, 0.0019 gigaflops per second. Now let's try that same Python implementation in Mojo. Here we are importing several packages. I won't go into the details here at this moment, but I will address this in my Mojo series that is coming up that I haven't officially announced yet, but you can expect an announcement soon. So we just copy and paste the Python code here. So let's go ahead and import these packages and then run the Python code. So now we benchmark the implementation. The matrix_init function indicates a new matrix with the given number of rows and columns. It defines several methods for the matrix, including the getters, setters, and an append method. Benchmark matmul untyped is a function for benchmarking the performance of untyped matrix multiplication. It then initiates three matrices A, B, and C. It then populates A and B with random floating point numbers between -5 and +5 and C with zeros. The function test_fn defined as a parameterized function which attempts to multiply the matrices A and B and store the result in C using the matmul_untyped function. The time taken to run test_fn calculates the number of gigaflops for the operation and the speed up over the Python implementation, which is passed as Python_gflops. Then the function benchmark matmul untypes is then called with arguments 64, 64, 64, and Python_gflops. This computes the performance of the untyped matrix multiplication with the Python implementation. So as you can see here, it's 0.027 gigaflops per second, which is higher than the previous value that we saw in the Python implementation, and it is about 14.24 times speed over Python. Okay, that's not bad, but is that the best that we can get out of Mojo? Well, let's find out. So let's go ahead and add types to the Python implementation. The above program, while achieving better performance in Python, is still not the best we can get from Mojo. Yes, because 14 times is not that high when they're claiming that Mojo is about 35,000 times faster than Python. So let's go ahead, optimize the code a little bit. Let's add the types to the Python implementation. The matrix struct has three fields: data, rows, and column. So let's go to Mojo documentation and see what struct type means. Struct types are similar in many ways to classes. However, where classes are extremely dynamic with dynamic dispatch, monkey patching, and dynamically bound instance properties, structs are static, bounded compile time, and inclined to their container instead of being implicitly indirect and reference counted. So the matrix struct type has three variables: data, rows, and columns. The init function is a constructor. It allocates a block of memory for the matrix elements, fills this memory with random numbers, and sets the number of rows and columns. The del function is a destructor that frees the memory when a matrix object is destroyed. The zero function sets all elements of the matrix to 0 using the memset0 function. The getItem and setItem functions are accessors that get and set the value of a matrix element at a specific row and column. They use the load and store functions, which perform SIMD, or single instruction multiple data operations. SIMD allows one operation to be performed on multiple data points simultaneously, which can significantly speed up numerical calculations. The always inline attribute on these functions suggests that they should always be inlined by the compiler. Inlining can also improve performance by eliminating the overhead of function calls, but it can increase the size of the binary. So let's go ahead and run that and just add type annotations matrix that we defined earlier. Now let's go ahead and benchmark the implementation again to see how much we improve. The next cell defines the generic benchmarking function benchmark that measures the performance of matrix multiplication functions. The function again is decorated with always inline, suggesting that it should always be inline by the compiler. The function takes four parameters: m, and k, which are the dimensions of the matrices involved in the multiplication, and Python_gflops, which is the performance of the Python implementation in gigaflops. In the function, three matrices A, B, and C are created with the specified dimensions. Matrix C is initialized with 0, then it defines an inline function test_fn that calls the provided matrix multiplication function func with matrices A, B, and C. The time taken to run test_fn is measured using a benchmark object. The reference to the data field of each matrix are stored in dummy variables to prevent the matrices from being destroyed before benchmarking is complete. The function then calculates the number of gigaflops performed by the matrix multiplication function, and the speedup is compared to the Python implementation, and these values are printed. Again, the last line of code calls the benchmark function. So let's go ahead and run these cells. Okay, so that's about 13 gigaflops per second. The performance improved compared to the previous benchmarking that we did, which was 0.027 gigaflops per second. And now we have 3.13 gigaflops per second. So it's about 1622 times speed up over Python. Okay, that's not bad. That's about 1600 times faster. All right, so now let's optimize the code a little bit more and see where it takes us. So let's vectorize the innermost loop. So this code defines a function, matmul vectorize 0, that optimizes matrix multiplication using SIMD, or single instruction multiple data operations. It processes multiple columns of the matrices in parallel with the SIMD operations. Any remaining columns that are less than the SIMD width are handled with scalar operations. So let's go ahead and run that and benchmark one more time. Alright, that's about 11.40 gigaflops per second, 5954 times speed up over Python. Not bad, not bad. I'm not going to go through the whole notebook in this particular video. I was just giving this a speed test and showing it to you guys how fast it really is. And if it is about 6,000 times, that's not bad at all. Now let's parallelize the matrix multiplication function. To get the best performance from modern processors, one has to utilize the multiple cores they have. With Mojo, it can be easily achieved using parallelize function. Let's modify our matmul implementation and make it multi-threaded. Now this one defines a matrix multiplication function, matmul underscore parallelized, that uses both vectorization and parallelization for optimizing this code. It uses the built-in vectorize function for SIMD operations and the parallelize function to perform operations simultaneously. The function calc underscore row is defined to compute each row of the result matrix C. Within this function, it defines the dot function to perform vectorized multiplication and addition operations for a given column. The dot function is then vectorized over all the columns of C using the vectorize function. The calc row function is then parallelized over all rows of C using the parallelize function. Again, the last line calls for benchmark function with matmul parallelized as the multiplication function, comparing its performance to the Python implementation. So let's go ahead and run the parallelizing matrix multiplication. Alright, so that is about 46.88 gigaflops per second, or 24,000 times speed up over Python. That is very impressive. It just gives a pretty excellent benchmark over Python. That was it for this video, guys. Thank you for joining. Please like and subscribe, and your support will be highly appreciated. Again, my goal for this channel is to build a very strong community of artificial intelligence, deep learning, machine learning, virtual reality enthusiasts. Please look forward to my announcement on my Mojo series. I'll see you next time. Cheers.